A logic gate is a very simple function that takes in binary inputs and generates an output. Logic gates can technically have any number of inputs, but it's up for debate how to implement them, and they typically just have two. However, they can only ever have one output, no matter the type. There are different kinds of logic gates too. The one shown here is called an AND gate. Its function is pretty self-explanatory. If A and B are both 1, it'll output a 1, but if only one or neither are, then it'll output a 0. There are three simple logic gates: AND, OR, and NOT. OR will output a 1 when either or both inputs are 1, and a NOT gate is just a basic inverter. Give it a 1, and spits out a 0, and vice versa. If you've done any programming besides Python, you'll know that logic can also be typed like this. This is how I will be writing them for the remainder of the video because I don't really feel like copying and pasting blurry JPEGs, and it's easy to forget what each gate looks like. Okay, so you understand what a logic gate does, but how do we get algebra from AND, OR, and NOT gates? Well, brace yourselves because things are about to get a whole lot more complicated. Let's start with writing our different possible inputs and our expected outputs. If we're adding 2 bits, our output will be no more than 2 digits in length. If you haven't watched my videos on binary or know how it works, pause and go watch those first, or you'll be very confused. For our first scenario, 0, 0, we would expect an output of 0, 0. Because we're using an addition function, 0 plus 0 equals 0. For our next scenario, we would expect the output of 1 and 0 to be 0, 1. And the same with the inverse. This one's also pretty basic because 1 plus 0 equals 1, and the commutative property still applies in binary, so we can inverse it and get the same output. Now on to our last scenario. 1 plus 1 equals 2, but since we're using binary, we can't write 2, and instead have to carry over to the next bit. So the output of 1, 1 is 1, 0. Now time to make the actual function. For this we're going to need a new type of gate, called the exclusive OR or XOR gate. Exclusive OR is the same as a regular OR, outputting a 1 if either input is a 1, with the exception that it outputs a 0 if both inputs are 1. You might notice a similarity between this gate and our previous chart we made for the addition function, especially with these last bits. This will come in handy later. Unlike the simple gates mentioned earlier, an XOR gate can be constructed using other gates like this. Maybe writing it out will help. A or B and not A and B. Our first argument is a simple OR gate and covers the cases of 0, 0, 1, 0, and 0, 1, while our last argument causes the gate to spit out a 0 if the input is 1, 1. You can write an XOR gate like this if you're curious. Okay, now we can actually make our function. Since you can only get one output from a gate, what we can do is split our output into 2 separate bits and apply different functions to get each column. Our first bit is a simple AND gate, because it only outputs a 1 when both inputs are 1. Our second bit, if you remember from earlier, is an XOR gate, because it only outputs a 1 when the single input is 1. Let's write out our function. We start with our 2 inputs, A and B. It doesn't matter what order A and B are in because of the commutative property. If we apply the AND gate to both inputs, it gives us our first bit. If we then apply the XOR gate to both inputs, we get our second bit. Let's try an example. Let's add 1 plus 0. If we feed our inputs through the AND gate, we get a 0, because although the first digit is a 1, the second is not. We then put it through the XOR gate, and we get a 1, because the first input is 1, and the second input is 0. And there we go. 1 plus 0 equals 1. I'll highlight our inputs in yellow and our outputs in green. You can chain that function, what's known as a 1-bit adder, a bunch of times with some exclusive ORs to make 2 or 4-bit adders, and you can chain those together to make 8 and 16-bit adders, and so on and so forth a million times per second to make it possible for you to be watching this video. It's the basic building block of computer logic. It's the equivalent of describing a system with a single atom in it. You add another atom, and you say it's 2 atoms. Add 2 more, and it's 4 atoms. But there comes a point where it just makes sense to call them molecules. You chain a couple of molecules together, and you get a polymer, and so on. If a 1-bit adder were a penny, the device you're watching this on would be the equivalent of a pile of like 20 cars, times 1,000. At a certain point, it just doesn't make sense to count in pennies. Although, 20,000 cars worth of pennies would equal around $8 million, so maybe it's time we start measuring in pennies. If you enjoyed this video, make sure to leave a like and subscribe, as these videos take a lot of work and it helps out a ton. If you have any suggestions for what I cover next, let me know in the comments because I'm out of ideas. See you in the next one.